I'm Ercument Cicek, and I'm from Bilkent University in Turkey. Today I'm going to talk about privacy challenges in genomic data sharing. Inspired by Layla, I just put this slide on where Bilkent University is. It's right at the heart of Turkey. So it's 11,000 kilometers, I guess, away. So this might be a way to visualize where we are and where Bilkent University is. So I'm going to talk about the genomic privacy issues. So, why is genome so private? It tells a lot about us, right? It defines us. And even more than that, maybe it might be defining what our children does, right? So half of their genome comes from you. So think about posting a picture of your child on Instagram. It might be an issue in the future. So think about sharing your genome, then your children might sue you in the future because this might be an issue with insurance, right? In US, so technically they have to insure you and make health insurance, but they can deny certain types of insurances just based on your genetic profile, so if it's available. So I'm sure you have heard about 23andMe issues. So they are about to go bankrupt last time I checked. And so they don't know what to do with the data. It's quite valuable, it's going to be transferred. What's going to happen? They have consent. So some people have already deleted their data, but it's just don't know. I mean, most of the people are not aware of the issue, and probably it's going to be sold and transferred to the new owner. Yeah. So I hope I convinced you that there's an issue with genome sharing, but this doesn't mean we should not share our genomes. It's a critical point for all the research that we are doing here, but we should be careful when we share the data. So GA4GH is a community effort which is trying to put standards on genomic data sharing. So in, I think 2015, they came up with this standard called the Beacon protocol. So it's a very simple protocol which basically tries to minimize the shared data, so it minimizes the risk of data leakage and these privacy issues. So it's a very simple protocol. So when you have a genomic data set like this, which is called Beacon, and there's a user which is interested in this, getting access to this data set, so they will pose a query. So is there anyone in this data set which has this alien? And the system answers simply yes or no. Actually, the new standard also can answer with the minor value frequency. So they say, 5% of the people have this alien, for instance. So they have a very nice central interface. So for instance, we are querying for the mutation on the BRCA gene, and it queries all the data sets in the background, all connected to the system, on this variant in 8 of these data sets. So, I mean, this is very nice because, you can query multiple data sets easily. So it encourages collaboration. And, apparently it's also minimal responses to these yes or no queries, right? So, I mean, by design, it's not supposed to leak information. It sounds privacy preserving, but it's not. So I'm going to talk about the issues with this protocol and why this leaks information and what can we do. So I'm going to talk about two types of attacks that have been shown against the system. So the first one is the membership inference attack, where we try to find out if a certain individual is in this data set or not. And this might be important because these data sets are usually associated with a sensitive phenotype. The second one is, can I reconstruct portions of the genome of some person just by relying on the answers of the system, which it's not supposed to leak by design. How many of you have heard about this case, the Golden State Killer? Can you raise hands? Okay, quite a lot. So maybe half. So if you don't know, so this person has committed numerous crimes back in 70s to 80s. So numerous rapes, burglaries, and so the police has DNA from the suspect, but they cannot find anyone for years. But they keep searching. And so there's no match in the data sets. And then I think in 2016 or something, so they use this GED match, which is a website where you upload your DNA, and then you are trying to find relatives. So the police uploaded the DNA of the suspect and found the relatives of this person. So he was a police officer, and by this search they narrowed down the search to like 1,000 people, to get about millions of people. it came down to 1,000, and then they found the person. So this is an example of a membership inference attack. For this time, it worked out good, but if it was you, maybe it's leaking your information, and it's violating your privacy. So in the first type of the attack, this membership inference attack, we assume the attacker has access to the VCF of the victim, meaning somehow it's stolen, so maybe through another leak somewhere. So, and then it keeps querying the system for the SNPs of this person. And if it gets enough evidence, then finds out that this person is in. And the second one, it keeps querying the system for snapshots of the system. Actually, I'm going to talk about this. Now, it doesn't have the VCF of the victim, but some auxiliary information about the victim, and it is trying to reconstruct the genome of this person. So first, I'll talk about the membership inference attacks. Here, again, the attacker has the VCF, keeps querying the beacon, and tries to find out. So this is the alleles of the victim. Some of them might be hidden because the victim has not shared with the system. So it finds out the heterozygous positions, queries the system, and if it receives enough yes responses, they conclude the person is in. So this is based on a very simple likelihood ratio test. Just to describe this, we have two hypotheses here. Null hypothesis is the victim is not in the beacon, and the alternative is they're in the beacon. So this is the log likelihood of the null hypothesis. So I have n queries, so I'm summing over n queries. Xi is the response of the system. If it is 1, it means there's at least someone in the system with that variable. And here the n is the probability that none of the n genomes in the system has this allele. Okay? So if I receive 1, it means the probability 1 minus the n has happened, right? So if I receive 0, then it means none of the persons has this allele. So I get log d. And the alternate is very simple answer. So I'm basically compute a statistic which is called the LRT statistic. And if based on the control group, if it is low enough or high enough, depending on how you define it, you can say, okay, this is unlikely that by chance this person is in the system. So this is called the likelihood ratio test. So this paper from 2005 was the first to show that there's such a risk in beacon sharing these responses. So they show if you have a data set of 65 individuals, if you select randomly 250 queries of this person, you can decide with only 5% false positive rate that this person isn't. Okay, so this was the first word. Then came the second word, where the first attack, SP attack, picks the SNPs randomly. This one orders the SNP with respect to their MAF. So if it's a SNP with a lower MAF, then it's giving you more information, right? So they order this time the alleles, as you see over here. Again, some of them might be hidden. Maybe the victim didn't want to release these SNPs that are very precious, kind of, so that are unique to them. So the attacker in this case queries the system in order of the MAFs, ascending MAFs. And again, it's based on a very similar likelihood ratio test. So this time, the lines are not that much important, but here you see this green line here means if I ask less than 10 queries of this person, but only the lowest MAF queries, then I can decide with less than 10 queries if this person is in or not 250. This is called optimal attack from 2017. All right. So what we did then, we thought, I'm going to talk about the defenses against this. One of the defenses is maybe if a person receives too many queries about themselves, maybe you should not answer any queries with that person, meaning take that person out of the system. So what we showed with Nora and Arman back in the day is, so when I ask a query, it is that SNP is correlated to other SNPs. So even though I ask one query, with a certain probability, I know the answer of the query that I didn't ask. Right? So, And so this is the first thing that we consider. And so this is called the query attack, and then the GA attack is concerned with what if I can also unlock the synapses that are hidden by the victim. So then we build a high order Markov model to using the k-neighboring range SNPs of these really rare SNPs to find out if they are ready in the genome of the victim. So for the query attack in this case, the likelihood ratio test is very similar to the original formulation, right? But in this case, for every query I ask, I receive some evidence for n more. So all those correlated queries with every query I ask, I receive more evidence for n correlated queries. And here gamma indicates my confidence in those additional evidence that I get, which is the correlation. So what we showed here is that this is very effective when the victim is actually hiding their rare SNPs. So this line over here you see is the optimal attack when the victim has hidden the SNPs with minor frequency less than 0.43. So then this attack requires around 400 instead of 10 queries. But when we use the correlations, we require only 300 queries. And what's really interesting is that if we are able to unlock those hidden SNPs, then we only require 5 queries instead of 400. So we show that using the correlations among variants, we can learn much more from the beacon protocol, which is not supposed to leak any private information. All right, so this was a kind of a fast summary of the membership inference attacks in the literature. Now I'm going to talk about the genome reconstruction attacks a little more. So I'll talk about the work from our group again. So the goal of the victim in this case again is to reconstruct the genome of a person that he knows is already in the dataset. So here, in this protocol, the attacker is in the group of regular users, hidden basically. So they take a snapshot of the system. Basically, query for every single SNP they are interested in, potentially large set, and take a snapshot. Then the assumption here is that they know the victim joined the study at time t plus something, right? So then take a second snapshot after that time. Then some of the answers have flipped. This means if you add a group of people into the system, which is happens quite often, then if you take the diff of the 2 snapshots, you can learn the SNPs of the people have recently joined. It might be more than one. So if it's just a single person, that's easy. But if it's more than one person, then it's a little bit more complicated. But still, we can work with it. So what we do is we find all those SNPs which have changed the answer. Then we do a clustering with respect to these correlations among SNPs again, and construct like n prime partial genomes. Okay, so which one of this is the victims? So we built models using the SNP dataset to predict some public phenotypes, public information about this victim, like eye color, hair color, which you can assume is already known by the attacker. So what we do is we input these partially reconstructed genomes into these models, and it predicts the eye color, hair color, and we know which one belongs to the victim with high performance. Now, what am I going to do with this reconstructed genome? So if you assume this is a data set which has no sensitive phenotype associated, so it's not really a big deal, but when I reconstruct the genome, I can use the genome to launch a membership inference attack. Even though I don't have access to the VCF of the victim, I can find out if that person is in a data set with a sensitive phenotype. So we show this works. So there are certain limitations of this genome reconstruction attacks. As I said, there are many assumptions that I listed. I need to take the snapshot of the victim of the data set. I need to know the time when the victim joins or leaves the set. So these are really strong assumptions. There are 2 other works which I didn't mention, but they rely on basically integer linear programming to find out the content of the data set. The problem is they are looking for an exact solution and they don't scale. So you can basically reconstruct only 10 to 50 variants of a person. So, and they assume the haploblocks and haplotypes in the system are all known, which might not be the case. For instance, OpenSynth is a quite a mixture, so you cannot run these attacks on such datasets. So this is a recent work that we had done, which is called the Beacon Reconstruction Attack. So instead of genome reconstruction, now I'm trying to reconstruct the full content of the beacon. So the question we are asking here is that, can we design a virtually assumption-free attack and just rely on the responses of this system and try to reconstruct large portions of this system for everybody in the beacon? So the question is, does the beacon protocol leak more information than previously thought? So we have a very simple algorithm. Actually, we teamed up with my colleague Saleem and a student from her group, Boza. So this is what we want to get. So we have a target SNP set, potentially a large SNP set, and for n individuals we want to fill in this table who have these SNPs and who don't. So we take a snapshot of the beacon, we ask the question to this beacon. So this is the actual data set. So we are not interested in these SNPs, but these are the ones we are interested in. We take a snapshot and the beacon responds with either binary responses or the allele frequencies. So we later show that this is quite revealing actually. The protocol must follow binary answers. Okay, so once we get these allele frequencies, we initialize the table such that it obeys those allele frequencies. For instance, for the first net, I know 40% of the participants has that, so only 2 people have been assigned. So this we say is the baseline algorithm. And so it obeys the allele frequencies, but doesn't care about the correlations between the SNPs. So the second step is to optimize for the correlation. So I use basically the loss function to. Oops.
What's the matter with
push buttons? Yeah, I pushed one button.
I think the play button.
Works. Okay. So I optimize this table to obey these correlations. So once I did that, now the allele frequencies are messed up. So this goes into a loop where we optimize for the SNP correlations and optimize for the allele frequencies until it converges. A very simple algorithm, but it works. So we worked on the HubMed European population, OpenSynth dataset, and also an Indian population too. So to see if the model also works for minority groups. This is the beacon size on the, so this is the OpenSynth dataset, this is the HubMed dataset. On the y-axis you have the F1 score of the attack. This is the baseline algorithm that you see over here for all the dataset sizes, which is basically just using the beacon response and initialize the table with respect to the allele frequencies. But once you optimize for the SNP correlations, as you see, we have about a 0.7 F1 score for a data set of 50 individuals, which is quite high compared to our baseline. And this is a regular, usual data set size in the literature to consider. So the result is same for the HubMed data set as well. So, and we reconstructed the genomes of 50 people for 1,000, which is a very large number compared to the literature. Then we checked if, what if the beacon only gave us binary answers. So this is what you see over here. Then I just estimate the allele frequency using the population, if I have the population information. But as you see, the performance drops significantly in this case, around slightly above 50%. So we suggest that the system should not report allele frequencies. This is as if I use Mexican population for some totally bogus population to imitate the allele frequency. It doesn't work at all. So this is still high, but the allele frequencies are the Achilles heel of this system. So we also did the same attack, tried to find out if when we construct the reconstructed genomes, can we use these for some other attack? So we construct a beacon with no sensitive attribute, launch our attack on the system. So we reconstruct this beacon. We have the reconstructed genomes of everyone here. And I have a second beacon, totally different set of people of 49, of size 49, I add one record at a time to have a beacon with 50 individuals. And using the reconstructed genome of this person, I launch a membership inference attack. Try to understand if that person is in that dataset with this noisy reconstructed genome. So we found out of 50 attacks, 41 of them were successful with 21 queries. So usually, the optimal attack would require usually like 10 queries. With double the number of queries, like 20, we were able to have like more than 80% success rate. So if you increase this, it actually gets even more successful. So we showed the protocol is leaking information. So I want to mention some of the defense strategies against this that are mentioned in the literature. So these are earlier ones. So they suggest having a larger beacon size. Okay, if we have more individuals, we can. You can have some alteration strategies like answer as if two people as it's like k-anonymity, if you know what I mean. So if you have at least two people answer it, but then this reduces the utility of the system quite substantially. So you might have random flipping strategy, which is again degrading the utility quite substantially. And this is what I was talking about earlier, the query budget per individual. So if a person is specifically hit, maybe take them out of the system. But we showed, for instance, for this individual, when you assign a budget as suggested in this paper, you have a budget of 6 queries hitting this person. And the optimal attack they propose requires 7 queries. So, before being re-identified, this person is out of the system. But when we use the correlations between steps, the number of queries required drops significantly. So our attack required 5 queries. So this doesn't really work all the time. So back in the day, we investigated what it be for every person if we add the relatives' genomes into the system. Since those genomes overlap quite a lot, you are going to add some noise to the system, but you are going to flip less queries. So it's going to have higher utility. So this is what we had shown. But again, so you are also putting somebody else who doesn't have the phenotype into the system, which is, again, degrading utility. So these are relatively newer systems. So the first one is strategic flipping. You flip if a query is quite valuable, like a recursive. But again, this degrades utility again. There is a method which considers differential privacy. It assumes that all these queries are provided in batch, which is not realistic. If I'm an attacker, I keep asking queries after I get a result. So it's like a follower, a leader and a follower game, right? So the assumption is not that realistic. So this paper actually proposes game theory. All the attacks and the defense I told you so far assume a certain static strategy. This says, okay, what if it changes? So they model the game as a Bayesian game and then play the game using 2 neural networks because you cannot compute the optimal strategies. The search space is huge. So every user is treated as a potential attacker and finds the game, this 2-player game, which is like a GAN-like game, decides for which steps I should add noise. So before the systems, I decide which steps must be flipped. Okay, but this is not that good because it is not adaptive. So the attacker might see that this is the strategy, so they might change along the way. So they might adapt. So that's what we proposed. We proposed 2 solutions to this problem. The first one is again game theory, but using a Steckelberg game, which is a more realistic solution. Like the first the attacker moves, or the user, and then the beacon decides if it should flip. And then the attacker sees this, takes another action, and the strategies might change. And the second one, so we showed this is good, but it doesn't scale again. And we modeled the game using reinforcement learning, where the defender, the beacon in this case, decides, tries to find out if this is a regular user or if this is an attacker, and adjust the honest rate of the system. So this is an addition or a suggestion from us to incorporate into the so here we have authenticated online setting again. So I know so people need to authenticate first, so I can keep track of their previous queries. The queries are sequential. So we define the privacy as, so we have a control group, another set of people, which so the privacy of a person is the fraction of the people who look more suspicious than this person that I'm interested in. So that if everybody is more suspicious than this person, I retain their privacy. And the utility of the beacon is the honesty rate. So you need to have the system as honest as possible. So that it's useful. Otherwise, you can just keep lying all the time. It doesn't make sense, right? So this is this shows that when I have 7 possible queries, which is very small, the system converges in finishes in 100 minutes. And if I have 8, it jumps. So this is the game theory-based solution. It doesn't scale. So we designed the reinforcement learning-based system, which relies on summary statistics of the data set it tests. So I train an agent given a data set, and it learns who is an attacker and who is a user based on the query behaviors. So the attacker can do anything, even ask queries who doesn't belong to the victim, just to deceive the system. So it observes them all and decides if there's an attack, and it should start to lie and decrease the honesty level. So we have states, like we have the utility of the beacon, MAF of the queries, numerous summary statistics about the data set and what has happened so far. And the actions, the beacon selects the honesty rate, the attacker selects a slip to ask. So it's a two-player game. So we have intermediate rewards. The beacon is rewarded if victim's privacy is retained and it's honest. The attacker is rewarded if the system is honest, because then it's useful, it's learning from it. Otherwise, it's just pure noise. And there's a final reward. The winner gets higher. So if the attacker identifies the victim, huge reward for him. If the beacon retains the privacy of the person and keeps high honesty rate, a big reward. So these are the protocols that we had used to train the system. Anyway, let me jump to the results. So this is here you see the utility and the privacy of the system for various queries asked to the system, right? So the one on the top, which we call GBD, is an agent which has learned to play this game against any user, regular users or any attacker that has any strategy that is observed in this training data set. So as you see, it keeps having the highest utility and privacy level among others. And here you see some bars. So this means after 100 queries, the first honest beacon let almost all of the individuals in the system being re-identified. Whereas we don't see any bar for our system, which means it retained the privacy of every single person in the system. So this is similar, but what I'm showing you over here is the regular user utility. So the system was, again, the red bar was able to identify who is an attacker and who is a regular user. So if it doesn't see the pattern it has learned in its training, it doesn't flip. And it doesn't adjust honesty rate, so it keeps being used. So it retains the utility for the regular users. Okay, I think it's time. So what I tried to show you is that genome sharing is good and might be also risky. So we have been working on this protocol, frequently used to share genomes and show that it might have some privacy risks. So I presented this last week to the Beacon people. So we are trying to work on such systems to be implemented into the protocol to preserve the privacy of the people. So what we showed is that the early frequencies might be too much for such a protocol to release. It's too informative and reinforcement learning method. So I'd like to thank the team funding and thank you for listening.